So today's session will be a continuation of the probability. In the last few sessions, what we discussed was we started with the importance of statistics in real life, and then the center and spread of the data. Right in the center. So in the session one, basically we covered the importance of stats in real life, including application in real life and data representation, interpretation, how to interpret it. And we also covered the charts, graphs, and the tables. Right. So session two, it was more on the center and the spread of the data. So we wanted in this session we discussed about the mean and the median, uh, and then for the IQR, interquartile range, and standard deviation. We moved on to Z score and closed the session. The last session was on probability basics. We started with the history of probability. We covered other technical terms, which is random experiment. Uh, yeah, we covered the random experiment, elementary outcomes, and the sample space. And then we saw what are the ways in which we are measuring probability: classical probability, relative frequency, personal probability. We saw a comparison of objectivist versus Bayesian, and then we covered events. What are events? We saw the conditions or and not events, and then we saw what are the mutually exhaustive events, and then we moved on to the conditional probability. So we covered conditional probability at a very basic level. So we'll be continuing after this. So this will discussed in the last session itself. So conditional probability is the probability when one event is measured after another event. Okay. So we'll see with an example. Suppose we are rolling a dice. We are rolling a dice twice. Okay. Throw one, throw two. So now, if earlier, if let's say the event was that the faces should sum up to three, right? So in that case, the probability, the sample space would be 1 to 1, and so the simple probability would be 2/36. Probability of A. A is our event of getting a sum of three, right? But now, for if I talk about conditional probability, I will say that my white die, basically, which is the first die which I roll, it already has a 1. What is the probability of A now? Now the probability of A is going to change. The reason is we already know that there is some number on the dice on the first die throw, right? So this is what we call the conditional probability. In technical terms or in mathematical form, how we represent it is P of A given C. So how we read it is probability of A given C has happened, right? And we call it and we say the probability of A given C, right? So if you go back to that event that we were just discussing, so the event A is getting a sum of three, and the event C is getting one on the first die, right? So this is the form that we use in stats or maths. Okay. Now let's see what are the how does the sample change, the sample space changes in both the let's say both the scenarios where condition was not there and when the condition started appearing up. So let's say before we are throwing any dice, the sample space already has 36 outcomes. Okay, 6 outcomes on first die, 6 outcomes on second die. So overall, it will have 36 outcomes, and so the sample space size would be 36. But now, since the event C has occurred, meaning there is 1 on the first die, so the sample space will reduce for A given C has happened, right? Let's see how it reduces. So if we draw in terms of visuals, if we draw for the event A given that C has happened, so this first row, this is the event C, which is getting 1 on the first die, and event A is getting a sum of 3. So now the sample space becomes all this. These 6 outcomes are there in the sample space. So on the first die you have 1, then on the next one you can have 1, 2, 3, 4, 5, 6. So the sample space would have only 6 outcomes, right? So that is the difference that we saw in the sample space for normal probability and for conditional probability. Now, in this, the only outcome which will satisfy my event A is this event 1 and 2, because this will sum up to 3, and my event A is the sum of 3, right? So the probability, if we calculate from this sample space, is 1 by 6, right? So that is what they are saying here. Now, again, if you remember, I mean, just a bit humorous side of it, this guy is still looking for his shirt. But this person is saying, this is the statistician, by the way, and he's saying, now we are getting to see how is the world of probability evolving, right? Also, in general, to find the conditional probability of E given F has happened, we look at the event E and F as part of the reduced sample space F, right? Uh, the basic difference between normal and conditional probability is when when you are trying to calculate conditional probability, your sample space is going to reduce. That's why we need some equations that we'll see later to calculate the conditional probability. Now, coming to the representation of this, um, okay, I think we have missed something here. Give me a minute. Yeah, let me share again. Sorry. Yeah, so now all of this can be translated into formal equations, okay? And we say that the probability of E given an event F has happened, probability of E given F is equal to probability of E and F. This and is the same condition that we discussed in the last session, divided by the probability of F, okay? So this is the formal equation that we should always remember for probability. Probability of E given F is equal to probability of E and F divided by probability of F. The denominator, the basically the event which has already happened, F will be the one coming in the denominator for RHS, right? So this is the equation that you should always remember. We have already seen how this equation will come for conditional probability. Now we should try to think of it as the basic of conditional probability, the root or the foundation. Okay. Now let's see how it fits into the dice equation, right? So in that, if you calculate the probability of A given C using this equation, it becomes probability of A and C divided by probability of C. right? Your C is getting 1 on the first dice, so the probability of C will be 1 by 6. And your A and C, right? A and C meaning C has happened, and then what are the chances of A and C occurring together? Getting a sum of 3 and getting 1 on the first die. So that will be 1 by 36, right? There can only be one outcome out of all the 36 sample spaces where C and A can occur, right? So using this equation, the probability of A given C becomes 1 by 6. So the same probability that we had calculated after looking at the sample spaces, reduced sample spaces for A, we could calculate from the equation also, right? This is how we could calculate. Moreover, this brings us to some of the conclusions that we can derive from this equation only. So we can say that if once E has occurred, right? Once E has occurred, then obviously the probability of getting E is sure shot. It's 1. So probability of E given that E had happened will be 1. Moreover, if E and F are mutually exclusive, right? So in that case, we can say that probability of E given that F has happened is going to be 0. The reason is, if you go back to this equation, probability of E and F is probability of E and F. So if they are mutually exclusive, your numerator will become 0. And once your numerator becomes 0, this probability of E and E given that F has happened is 0. It's all derived from, both of these are derived from this equation. Okay, moving on. Now, if we go back to that equation, we had probability of E given that F is equal to probability of E and F divided by probability of F. Rearranging it, we will get probability of E and F is equal to probability of E given F has happened into probability of F. So the way I used to remember it was uh, whatever is in the denominator, the same probability will get multiplied, and you will get the intersection probability, basically E and F. Right? So this is again just a derivation of the above of the equation that we had discussed earlier, but an important derivation, I would say. Just a rearrangement, right? Now, let's say if you rearrange the events E and F, okay, so your probability of E and F and probability of F and E are going to be the same, right? Because there is just and condition, and the intersection of both the events is going to be the same. Whether you mention first, I mean the order won't matter there. So ideally, your probability of E and F will be equal to probability of F and E, which again will lead me to this equation. So if you take the RHS from both equations, it will become probability of F into probability of E given F has happened is equal to probability of E into probability of F given E has happened. All right. So this is one important. This is one more important thing that we can derive from the above. All right. Now we come to another concept called independence and how we can use the special multiplication rule. Okay. So we when we say two events, let's say E and F are independent, what we mean is that the occurrence of one has no influence on the probability of the other. Right. So again, reiterating this, if if the occurrence of one event has no influence on the probability of the other event, we call them independent events. Okay. For example, if we roll two dice, okay, so getting one on the first dice and getting one on the second dice, let's say these are the two events. So let's say these are the two events A and B. So since B is not dependent on the outcome of A, then you say that A and B are going to be independent of each other, right? Uh, and the scenario in which this can be different is, let's say, if they are glued to each other. In that case, you won't be able to have them as independent events. So this is what we mean by the independence of events. Uh, Moreover, if we say, I mean, going back to the same equation, the conditional probability equation. So if we look at this equation, probability of E given that F has happened will be equal to probability of E because they are independent events. Or we can say that probability of F will be equal to F given E has happened because again E and F are independent. So what we can say is probability of E and F is equal to probability of E into probability of F. Now this is a very important equation for the independent events. If two events E and F are independent, then we can say that probability of E and F will be a multiplication of probability of E and probability of F, right? So let's see and let's try to implement it. Let's see how it fits into our example, right? The dice one. We'll use the formulas. So C is the, let's say C is the event white die comes up 1, and D is the event that black die comes up 1, right? So the probability of C and D. So in here we can clearly see that they are going to be independent because both of the events says a 1 comes up on the dice, right? Now here if you want to calculate probability of C given that D has happened, so this is just going to the formula. This is just going to be probability of C and D upon probability of D. So, and you get 1/6, right? So now, but if on the white die it's showing 1, it obviously affects the result of, when we discussed the event A is getting a sum of 3. So in that case, the outcome of the first event will affect the event A getting a sum of 1. So in that case, we can't. Where is the pointer? Yeah. So in that case, we can apply this formula, but we won't have it. Okay, let's see what is the formula here. So there, the probability of A given C will be equal to probability of A and C divided by the probability of C. Now the probability of getting a 1 and a 2 is going to be 1/36, and probability of C is going to be 1/6. So this will lead to 1/6. Now the probability of A is getting a sum of 3, right? Getting a sum of 3, the probability is 2/36, right? Because the sample space would be 1, 2, and 2, 1. So if you divide it by 2, it will be 1/18, right? Now, what they are saying is that the conditional probability that we derived from the formula is 1/6, but your probability of A is 1/18. So that eventually means they are not independent. So that is one way of seeing if two events are independent or not. You just calculate the probability of a single event and then you just calculate the conditional probability. If they don't come out to be the same, they are not independent. If they come out to be the same, they are independent. Okay, so that is one check. Any questions up till this point? Gaurav, you are here, right? Okay. Moving on. So now we'll be summarizing all the formulas that we have seen yet. Okay. So the first one was the addition rule, basically where we saw if there are two events and we want to see the or condition basically between them, probability of E or F, it will be equal to probability of E plus probability of F minus probability of E and F, right? And as a special case, if the events are mutually exclusive, this is going to be zero. This is going to be zero in case of mutually exclusive events, and probability of E or F will be probability of E plus probability of F, right? So yeah, I will say this one addition rule. And then the second one was subtraction rule, where we saw that probability of E is equal to 1 minus probability of not E, which is a very uh, intuitive formula, I would say. Third is the multiplication rule that we just saw in the session. Probability of E and F will be probability of E given F into probability of F. Basically, the denominator will be the same. And the special case, when E and F are independent, your probability of E given that F will be equal to the probability of E only. So this formula reduces to probability of E and F is equal to probability of E into probability of F. Right. So I would say that this is a basically a summary of what all we have studied yet, right? So, and they are at the same time very important. Moving on. Now let's get back to like this guy, Demir, and this guy Demir, he's a gambler, and he was kind of so in session 3 we discussed about this guy's problem. The problem was with basic math. What he was getting was the probability of two events were almost the same. But what he had observed from his findings, from the countless gambles that he would have played, the one of the event was more likely to happen. So let's see from these revised formulas what we can derive. Okay. Now for him, let's say this is the event T, and event T is the event of getting at least 1/6 in 4 rolls of a single die, right? So he's rolling a single die, and we need and E is the event of getting at least 1/6 in the 4 rolls of single die. Okay. So let's see what is probability of E. So in this case, we are going to, instead of calculating probability of E, we are going to calculate probability of not E, which we can say E bar, which we have not studied yet, but that's also one representation. So now let's calculate the probability of E, and let's see how we can calculate the probability of E from this. Now, if AI is the event getting no 6 on ith throw, we know that the probability of AI is going to be 5/6 because AI is not getting a 6 on the ith throw. So uh, we also know, because since the roles are independent, so probability of not E is going to be uh, A1, A2, A3, and A4, all of them occurring together, right? Because it's a these are independent roles, right? So we'll just multiply the probabilities, and once we multiply all of them, it is going to be 5/6 into 5/6 into 5/6 into 5/6, which is 0.48. Now this is the probability of not. If we have to calculate probability of E, it will simply be 1 minus probability of not E, which is 0.518, right? So for the event E, the probability is 0.518. Let's come on to the other event, that is interesting pairing. Now the second half is, let's call it the event F, and here he wanted, the event was getting at least 1/6 in 24 throws. Again, in this scenario as well, we will find out the not F. Okay, that is not getting 6/6 in 24 throws, right? So please note here that the one throw means rolling two dice together. Now, if BI is the event that no double six is thrown on the ith roll, then not F is equal to not F would mean B1, B2, B3, B4, and so on till B24 occurring together, right? And probability of each B occurring is 35 by 36, right? Because getting a double six is just one of the outcome out of the 36. So BI is the event of no double six, so it will be 35 by 36, right? So probability of BI will be 35 by 36. So probability of not F will be BI into probability of BI into probability of B1 into probability of B2 and so on till 20 probability of B24. So probability of not F is going to be 35 by 36 to the power 24, which is 0.509. Now you have probability of not F. So the probability of F will be 1 minus probability not F, which is 0.491. So clearly, these two events are not having the same probability. So one was 0.518 and the next was 0.491. And hence, what Denier could see was the difference in the winnings that he had in both the scenarios. I hope it is clear. Moving on. Now, we also need to consider the case of the false positives in here and related to the Bayes theorem, right? So let's talk about some serious problems which we have in the real world. Let's say there is a rare disease that infects, out of every 1,000 person in a population, it infects only one person. That's an average that we have. And now suppose that there is a good test for this disease. If a person has this disease, this test comes back positive 99% of the time. Please note this figure 99%. So what it means is that out of the 100 results that you get, right? So 99% it will be correct. Yeah. Or no, sorry. I take back that statement. Let's say if a person has the disease, the test is going to come back positive 99% of the time. So if an infected person is tested, let's say 100 times, the chances are that one time you will get a negative result, right? So, in short, all the reports or the lab tests that we have all run on the probability. Also, on the other hand, uh, the test would also produce some false positive. False positive meaning if the person is healthy and you are diagnosing him as infected, right? So, about 2% of the uninfected patients also test positive, right? So, this becomes a bigger problem once you are into the government, or let's say if you are into hospital administration and all. So this becomes a problem that way because the people want to be sure whether do I have a disease or do I not, and so on. Now, in this case, we have two events to work with. If we look at it that way, we have two events. Event one, event A, is that the patient has the disease, and event B is that patient tests positive. Right? Uh, let's see what this person wants to know. This person wants to know, should I pay in advance? Meaning he wants to know whether he has the disease or he should start treatment for that or not. So coming back, we have made two events. Let event A be patient has the disease and event B be patient tests positive. Okay. Now, what all can we see from all the probabilities that we have? That the probability of A is patient having the disease. The probability is 1 by 1000, right? Because one patient in 1000 has the disease, so it is 1 by 1000, meaning 0.001. Now, probability of B given that A has happened, right? Probability of, we are just converting the statements into representation. Probability of B given A is 99% because the probability of positive test given infection is there is 0.9. Now, probability of B given not A is 0.0, meaning, so uh, if we do not have the disease, the probability of getting tested positive is 0.02%. Now, what we ask is, what is the probability of A given B has happened? Meaning, if the test has come positive, what is the probability that you have the disease? I hope you understand the problem. So we have all the equations here now. What we want to calculate is the bottom one, and for that we can use the equation probability of A given B is equal to probability of A and B divided by probability of B. And we can also use chain rules to determine the probability of B, probability of A and B, and so on and so forth. Right. So since we have probability of A and B given that A has happened, we can find out the probability of A and B from here. Moreover, since we have B given not A has happened is 0.02, we can see B given that A has happened, and so on and so forth. We can basically use all the equations and some equations over here. So this I will leave up to you as a homework. Okay, moving on. Now let's put whatever we have studied, all the equations and everything else uh, into one form. Okay, let's put the two together. And I want to introduce another term called a random variable here. The random variable is represented by a large X. So not this large. This would depend on the size of the notebook that you're writing in. Okay, but it's a capital X basically. And if you want to define it, a random variable is defined as a numerical outcome of a random experiment. Okay. Let's see what is a random variable in detail. Now, let's say we are tossing 2 coins, okay, and we record the number of heads in. Okay, so the possible outcomes. So the random experiment is tossing 2 coins, right? And what are the outcomes? The outcomes are either we can get tail tail, either we can get head tail, tail head, or we can get head head. And what will be my x? Because we want to count the number of heads. My x will be 0, 1 in both these cases, and 2 in this one case. Right now, for the notation, this variable containing all the outcomes for x, which is the number of heads, it is known. It is written as capital X, which is the random variable. Right. So the lowercase, I mean, here we are saying it a lowercase, but all of this is going to be capital X. And what does this lowercase x means? It means that what is the single value of capital X? What is the single value of my random variable? For example, x is equal to 2, small x is equal to 2 would mean heads coming up twice. Number of heads is 2. Right? So that is what we mean when we say small x and capital X. I hope this is clear. Now, let's look at these probabilities of all the outcomes. Okay, for the probability of the random variable x having any value small x, we write probability of x is equal to x or simply px. Okay, probability of small x. Right. So if we write it in terms of table, if your x is 0, 1, and 2, your probability of x is equal to x is 1 by 4, getting no head, 1 by 2, getting one head, exactly one head, and 1 by 4, getting two heads. Right. So this table is called the probability distribution of random variable x. This is very important. When we say the probability distribution of any random variable, what we want to say is what are the respective probabilities of every value of random variable. And once we plot it, we get the whole probability distribution of the random variable x. Right? Moving on. I hope this is clear. Now, let's try to draw some graphs, okay, or histograms, and we had discussed earlier. So if we draw the histogram on the x-axis, we will have the small x, basically number of heads, and on the y-axis we have the probability, right, px. So we can see that for 0 we had 0.25, for 1 we had 1 by 2, that is 0.5, for 2 again we had 1 by 4, that is 0.25. So this will be the histogram or the probability distribution. Now again, one more thing that we can see from here, that the total area of these boxes is 1. You sum all of it, it's going to be 1, because these are all the sample spaces that you have. Each box has base 1 and height px, so the total area is the sum of the probabilities, blah blah. If you want to calculate the area of the graph, you can just multiply the x and the y, right, the base and the height basically of all the rectangles, and then you will get 1. Let's take another example. So this time uh, we are the example is the toss of two dice. Okay, and we say that y is representing, the sum of the dots on the two dice. Okay, basically the sum of the numbers on the two dice. Now, for this random variable y that we have called, that we have defined, basically it can be any number between 2 and 12. Okay, this is understood, right? The sum will all, the minimum sum is 2 and the maximum is 12. So this random variable y can take any value from 2 and 12. Now let's try to do the same things as we did for the coin toss event. So in here, if we see y getting a value of 2, so getting a value of 2 would mean 1 on both the dices. So the probability will be 1 by 36. Getting a value of 3 is, for this, the favorable thing is 1 to 2 1, right? So probability will be 2 by 36. And if you continue like this, right, these will be the probabilities that you will get. So probability of getting 12, that is 6 on both dice, is 1 by 36, and so on and so forth. You will see a very symmetrical thing here. The probability goes on increasing. The probability goes on increasing till 7. Okay, and then it comes down to the same level. This is the law of the nature, actually. We'll see it later when once we study the normal distributions and other distributions. But from a very simple example of a dice throw, of let's say 2 dice throw, we have seen how the distribution of y, it follows a very symmetrical probability curve or distribution. Moving on. So if we draw a histogram for all the probability distributions that we have, uh, we will get something like this. Okay, if you can see here 7, this is having my highest probability, getting a sum of 7. So if let's say tomorrow you play a game with your folks or your friends and you want to bet on something, just bet on the number 7, getting a sum of 7 on the dice, and you will definitely win more, basically. Not every time, but you will win more. Right? So I hope it is clear. Moving on. Now we illustrate using the random variable x, and let's say there is one person who is very crazy about throwing coins, right? And he is recording all the outputs. Now what he does is he takes 2 coins and throws them repeatedly, and he keeps track of the results also, right? So this is the sheet that he has, and he is maintaining a log for, let's say, 2 heads, then 1 head, and then 0 head. Now, let's say what he has done is he has repeated the uh, experiment 1000 times. Okay? He has done 1000 tosses, and he has obtained some data. Okay, so okay, let me draw a line here. Let's see the observed data that he has from the experiment. What he is measuring is the number of occurrences. Okay, let's say of a head or a tail, and what he has seen is the probability of zero point 0.5 has occurred. Sorry, this is the probability model. So this is the value of the random variable x. Let's say head or a tail. So getting a zero, he got 0 260 times out of 1000. He got 1 517 times out of 1000. He got 2 heads 223 times out of 1000. So if he divides it by 1000, that is, if he wants a relative frequency, what he will get is 0.26, and then 0.1517, then 0.223. Now this is the observation that he has. Now if we go back to our basics, okay, if we go back to how we should get the probabilities, it is going to be, so the probability of getting no head will be 0.25. Okay. Now observe this 0.25 value is very close to 0.26. So here we are calculating, here we are doing the same debate that the objective is, and the statistician had in the previous session, right? Repeating the experiment a number of times, let's say 1000. So now that he has done it 10 times, now that when he has done for 1000 times, the probabilities are almost equal. I mean, they are very near. So the probability model would give me 0.25, but my empirical experiment that I have done, it's given me 0.26. Similarly, if we look at this value uh, for the random variable value 1, basically getting 1 head. So my probability model would give me 0.5, whereas what he observed is 0.517. Please note here that there are just 1000 tosses that he have made. And getting 2 heads, probability model says it should be 0.25, but what he observed was 0.223, almost close. So we go back to the original hypothesis that if you repeat the experiment n number of times where n is very large, the probabilities from the probability model and your observed probabilities are going to be the same. Okay, moving on. Yeah, and if you draw the probability histogram for the probability model versus the experiment that he has done, so the right histogram is the one for the empirical experiment that he has done, and the left one is for the probability model. Please see that the probability model will give you a very uniform graph, but the empirical experiment that he has done, it may or may not give you a symmetrical graph because it's just 1000 tosses, right? So if he was to repeat the experiment, let's say 1 lakh times or 1 crore times, this graph will, the right graph would slowly shift towards the left graph. Basically, more symmetry, basically, which is the root of the nature. Yeah. Moving on. So let's see. Since we have discussed random variables are just the all the outcomes of experiment, and we have seen that how we plot or how we calculate the probability distribution of any random variable. Now, the next step is to see what are the mean and the variance of random variables and why do we need it, basically, right? Uh, we'll talk about some symbols that we use. Okay, there is one popular symbol called mu. This symbol in maths, I think it's a Greek symbol. Mu, we use it for the mean. We had earlier used it for the mean, and again we'll be using it for the mean only here, right? Now, I will reiterate the difference between population and the sample. So, population ideally would mean everything. So, every data point which is possible is covered in the population. Whereas, sample is the data that I have obtained. Let's say thousand coin tosses. That is my sample, right? And my population will be, let's say, infinite number of tosses, right? So, whatever theories we have in probability, they are all applicable to population. But there is a beauty that we can get some of those to our, we can apply some of those equations to our samples as well, right? So that is the beauty, I would say. Yeah. Also, since they are all population properties, for the population mean, we use mu, and for the population standard deviation, we use sigma. Okay. And for the sample data, we use Roman symbols, which is X bar and S for the mean and the standard deviation. Smallest and X bar. Okay, this is for population. Mu and sigma are for, sorry, mu and sigma are for population. X bar and smallest are for sample. Now, let's go back to how we define the mean. The mean that we defined was simply X bar is equal to average of all the values, basically sigma of xi, where I varies from 1 to n, divided by n, right? Now, let's see how we can turn this equation around and see how it fits into the probability, right? Now, let's say some of these data points, xi, they have equal values. If they have equal values, how will your xi become is what we will see in the next slide, right? And for the example, let's consider the event in which they are measuring for the number of heads. So for the number of heads, the only available values are 0, 1, and 2. Okay. And the mad person, they have made 1000 process, right? And the value of 0 was taken 260 times. One head came up 517 times, and two heads came up 233 times, right? Now let's see how this sample mean would be in this case. So if we go back to this formula, okay, so this formula says that x bar is equal to 1 by into sigma x, right? Sigma xi, right? But since sigma xi had only three discrete values, 0, 1, and 2, I will just multiply it by its number of times it has occurred. Okay. So rearranging this, I would write the term inside my sigma as nx into x, where the sigma is happening over all the x. Nx would be number of times 0, number of times 1, number of times 2, and x will be my uh, 0, 1, and 2, whatever it is. So this will be my mean x bar. Or rearranging this term and taking n inside, we will get x bar as x and x upon n. Now this nx upon n, look at this term, nx upon n. So this nx upon n is the relative frequency only. And the relative frequency is none other than the probability of getting an x. So by analogy, what we can say is x bar is equal to x into px for all x, right? And this is what we call as the probability of the mean distribution. Okay? This is going to be a very important equation in the further discussions when we'll discuss about the probability distributions and so on and so forth. So just remember this equation x px. Moreover, here x is a discrete variable. That's why we are using summation. If x becomes a continuous variable, we'll be using integral. Okay, but that we'll see once we discuss the continuous random variables. Again, putting it in a more formal way, definition is the mean of any random variable x. Any random variable x uh, is defined as mu is equal to x px, right? So now here you will say, why are we switching to mu here now? Because all the px's that I will be determining will be based on the probability itself. So instead of getting x bar, we will get a mu. Mu is the mean of the population, right? Also, when we derive this mu, we call this as an expected value of x or ex. So this you will also study in the statistics 2 foundation course, right? What is the expectation of x? So expectation of x is nothing but the mean, okay? And think of it as the sum of all the possible values, each weighted by its probability. That's the simplest way to understand the expected value. Moving on. Now, for the coin tossers experiment, who tossed the coin 1,000 times, let's compare her sample with the model mean. Okay. So from the sample, so here I will draw a line. On the left side, you will see the sample. On the right side, you will see the model. On the left side, what are all the observations that she had made? Okay. So x 0, 1, and 2, these are all the small x values, basically number of heads. And nx upon n, the relative frequency is 0.26, and then 0.517, and then 0.223. And the value x nx upon n will be 0, because you will be multiplying it with 0, right? So it will be 0, it will be 0.517, then 0.223 into 2 is 0.446. You will again sum it up and you will get x bar as 0.963. Okay. So from your empirical experiment, what you did, you get an expected value of 0.963. Now let's look at the probability model, what it says. So from probability model, getting 0 head, the probability is 0.25. Getting 1 head, the probability is 0.5. Getting 2 heads, the probability is 0.5. Now, again, doing the same thing, calculating x, px, we get 0, 0.5, 0.5, and summating it, we get 1. So the population expectation would be 1. Please note that these values are very close to each other. And if you were to repeat this experiment infinite number of times, your expectation is going to be 1 itself. Right? moving on. Now let's do the same thing for the standard deviation. Okay, the or let's call it variance. Okay, standard deviation is s, so variance is s square, because variance is just the square of standard deviation. Now, if you remember the formula that we had discussed earlier, the standard deviation is going to be sorry, the variance for a sample. Please note, it's a sample. So variance for a sample will be 1 upon n minus 1 into sigma xi minus x bar to square, where I varies from 1 to n. Okay. Now, uh, I agree. I mean, this guy is right when he says more math, but yes, we'll have to dive into math at some point of time to, do brief representations and all. Now, this requires to measure the average square distance from the mean. So, we can rewrite this equation as x minus x square up into nx upon n minus 1. The same thing that we did earlier. X minus xi bar will be same for the observations which have the same number of hits, let's say same outcome. So, we'll be taking in uh, all of it, basically multiplying by nx, and then we'll take inside n minus 1, so it will come in the denominator here. So this is the equation for my standard deviation. Now let's see. uh, yeah, for the previous equation, except for the annoying denominator, which is n minus 1, right? So we can see here that the denominator is n minus 1, but somehow we are more inclined towards simplistic denominators like n, right? So here we describe another term called variance. Okay, and the variance of any random variable x is the expected square distance from the population mean. Okay, so sigma square, sigma is my standard deviation, and variance becomes sigma square. Sigma square will be sigma of x minus mu per square into px. Px is the probability or the relative frequency. Right? So this is the formula that we get for the standard deviation or the variance. So basically, both of them are interdependent, right? So the same thing. Uh, yeah. Moreover, if we look at this formula, right, sigma square. So sigma square, it kind of resonates with the expectation of x minus mu per square, right? Because expectation of x minus mu per square will be x px, and x in this case. See, I will rewrite the formula. The expectation was x into px, right? So whatever, so this is the expectation of x, right, is equal to x into px, and we summated sigma of x px. Now, if the event x changes to x minus mu per square, so this will become x minus mu per square into probability of x, and you will summate it over all x. So that is what the standard deviation is. Now, just an example. Uh, so for the coin toss, again, we have x as 0, 1, 2, we have px as 0.25, 0.5, 0.5, and we calculate a factor x minus mu square into px. So x minus, so mu is going to be 1, we had seen earlier. X minus mu square into 0.25 will be 0.25 itself, and here x minus mu is going to be 0, so that's why it's 0. Here it will be 0.25, and the summation would be 0.50. So your sigma square, your variance will be 0.5. Right? Now, To sum up, your mu and sigma, the population mean and standard deviation, are the properties we can compute from the probability distributions. They are completely analogous to the sample mean x and standard deviation as computed from the sample data. So what they are trying to say here is that you will have standard definitions of mean and standard deviation for the population, but we have a perfect analogy between the sample and the population, and we can relate them very well. So uh, from the probability equations we can find out mu and sigma, and we'll reach to the x bar and the standard deviation small s for the sample, right? So we will just introduce the continuous random variables. So up till now, whatever experiment we saw, it had a discrete output. Let's say number of heads, number of tails, or things like that, right? So the outcome was discrete. So the random variable capital X was our discrete random variable. Now, in cases where the random variable, where the outcome is not discrete, let's say it's 0.1, 0.101, 0.2345678, right? Things like that. So in that case, the random variable is continuous random variable, right? Now let's imagine a random experiment in which all outcomes have probability zero. Yeah. So that's a bit tricky. Let's say probability of x is zero for every x. So what happens there? We'll discuss it more in the next session. I leave it. I leave the session here. I conclude the session. I hope we don't have any questions. Please post on the group if you have any questions on this, right? And I will reply on those.